All right, you guys, so today we're looking at scale factors and areas of two-dimensional shapes. So last time we kind of looked at scale factors, but we were just talking about linear measurements. So now we're going to look at two-dimensional shapes. So I'm actually going to kind of skip this first part to start out with, and we're going to go right to this investigation, and then we'll come back to what these key ideas are, because the investigation kind of leads us into that. So when we enlarge or reduce an object's dimensions, we affect the area by a related factor, and we kind of want to determine what that factor would be. So let's use a square, so a two-dimensional shape, in order to kind of explore how these factors are related. So if we're given the side length of a square here, we know that we can calculate the area of a square by doing the length times the width, right? Which is basically, or just the length squared, you could actually say, because with a square the side should be the same length. So if we have a side length of 3 centimeters, then we know that's going to be 3 times by 3, which will give us an area of 9 centimeters squared. So remembering that whenever we have area, our units are always squared, because we had to multiply the two lengths together. So then if we have a square with side lengths of 4, we know we're going to have 4 times 4, which will give us 16 centimeters squared of area inside of this square. If we have 9 centimeters, we're going to have 9 times 9, or 81 centimeters squared. And if we have 10 centimeters squared, we're going to have 10 times 10, which is 100 centimeters squared. So pretty straightforward. Now, if we take our original squares that we had here and we want to change them by a scale factor. So in these first two, we're changing the side length by a scale factor of 2, and keep in mind that means we're basically doubling the side length. So essentially what we're going to have is 3 centimeters times by 2 for this first one, means that our new side length is going to be 6 centimeters. Right? So these are going to be fairly straightforward, so I won't write the math out for all of them. For this one, we have 4 centimeters times by 2. Actually, you know what? Because I'm going to post this, I might just quickly write it out. 8 centimeters will be our new side length. Now, for a 9 centimeter, if we have a scale factor of a third, keep in mind that means we're either doing 9 times by a third, or you can think of it as 9 divided by 3. So 9 centimeters times by 1/3 is going to give us a side length of 3 centimeters. And last of all, we have 10 centimeters times by 1/2, or divided by 2, either way, whichever you're more comfortable with. And that's going to leave us with a side length of 5 centimeters. Okay, so all of that is pretty straightforward and basic math. But now we want to look at how this is affecting the area and then see if we can find the relationship here. So we want to look at the new area of this square, which is basically just going to be our side length squared again, right? Our new side length squared. So in this case, we're going to have 6 times by 6, which will give us 36 centimeters squared. In our next one, we're going to have 8 times by 8, which will give us 64 centimeters squared. And in this one, we have a new side length that's shorter, right? So it's 3 centimeters squared, or sorry, 3 centimeters side length. So if we square that, we end up with 9 centimeters squared. And then last of all, we had 5 centimeters. So that ends up giving us an area of 25 centimeters squared. Now what we want to think about here is, what is the relationship between the scale factor and the new area, right? So if we compare our original area and then we look at our scale factor and then our new area, you'll notice that when the scale factor is 2, it's changing the area of the square with that has an area of 9 centimeters to 36 centimeters. So if we remember always when we're dealing with scales, we're thinking in terms of multiplication and division. So if you think about 9 and 36 in terms of multiplication or division, what's the relationship? Well, you probably know that 9 times 4 is 36 centimeters, right? And so essentially what we end up having is that the scale factor, which was 2, if we square that, so 2 squared is 4, now we find that using the squared scale factor, we can go between the two different areas, the original area and the new area. Let's see if that holds true for the next one. So in this one we have 16 centimeters squared was our original area. We have a scale factor of 2, but because we're dealing with area, which is a squared unit, we want to do 2 squared, which would be 4. And so if we look at that, 16 times 4 does in fact give us 64. So that holds true for that one as well. All right, now these ones are a little bit trickier because they are fractions. So remember that if we square a fraction, then basically what we're doing is, I'm just going to grab a little piece of scrap paper here and show you. Remember that when we square a fraction, so in this case we have a fraction of 1/3. So basically that means we're multiplying 1/3 by itself one time, right? Remember, when you multiply fractions, you multiply straight across. So 1 times 1 gives us 1. 3 times 3 gives us 9 as our new denominator. And so what we kind of want to think about here is, okay, so if we have 1/9, then basically we want to think about if we do 81 divided by 9 or times by 1/9, it's the same math, do we get 9? Well, yeah, we do, right? 9 times 9 is 81. So if we divide 81 by 9, we should get 9, which is what we see here. So now we can see that this is still holding true, where if you square the scale factor, even if it's a fraction so that we have a reduction, you still can use that squared value to move between the original value and the new value for the area. The last one we have here is 100 centimeters squared. So if we were doing 1/2 squared, remember that would be 1/2 times by 1/2, which is going to give us 1/4. So essentially what that's saying is, if we do 100 times by 1/4 or 100 divided by 4, do we get 25? Well, we do, right? And so again, we see that we're moving between the original area and the new area by squaring the scale factor. Okay, and so that's essentially what we're talking about up here under this section of key ideas, which is kind of reviewing some stuff we've already looked at. So if you remember, we talked about how with a linear length, you can take the scale factor and multiply it by the original length to get the new length, right? In this case, the diagram sides. So now, because we're looking at a 2D structure, this will hold true for any side of the structure that we're looking at. You multiply the original by the scale factor and you get the diagram length. Now with area, what we just figured out is that you can do kind of the same thing, where you can take the scale factor squared, multiply it by the original area, and you will find the new area of the diagram. Okay. This part down here is basically just showing you how to rearrange if you need to solve for the scale factor, right? So if you have, for example, like the diagram in the original lengths and you want to solve for scale factor, so scale factor is essentially always diagram divided by original, which we talked about before. With area, we have kind of the same setup, right? It's the scale factor squared is equal to diagram area over original area. So you can see the similarities here, and hopefully that will, if you can kind of keep that in mind, it will limit your need to memorize a lot of different things. You just need to remember that with area, we have the scale factor squared. And then that also means that if you're actually trying to solve for just the scale factor, remember, then you can't have that squared component there, which means you need to get rid of it. Algebraically, we do that by square rooting this side. So if you square root a square, the square is kind of undone, but you need to do that to the other side of the equation as well. So we find that the scale factor for area is going to be equal to the square root of diagram area over original area. For me personally, if I was doing like, studying for a test or whatever, I would just remember this component because I already know the algebra to get to that if I need to, because I don't want to be like memorizing a bunch of extra material. Okay, so knowing this information now, let's work with some practice problems. In this first one, it says Sophie is making a window covering from a 3 to 30 scale diagram. So the area of the scale diagram is 25 centimeters squared, and she needs to know how much material she's going to need in order to make her curtains. So with this one, because we're given kind of like an odd scale, I would personally just first of all convert it into a decimal because it's going to be easier to work with. So I would say my scale factor is going to be equal to 3 divided by 30, which is going to be equal to, if I do the math for that, it's going to be 0.1. Okay, so excuse me. Now what I want to do is I have my scale factor, and I also already have my diagram area. So what I need to solve for is my original. So if we think about how this equation would be set up, it would be scale factor is equal to the diagram divided by the original. And so when we look at how this is set up, we know that we can solve algebraically because we already have the diagram and the scale factor. So we just need to solve for the original. So here it's kind of just a matter of what you're more comfortable with. Personally, I like to do my rearranging before I start putting numbers in. Oh shoot, actually, sorry guys, because we're dealing with area, this is going to be scale factor squared is equal to diagram over original. Okay, and so what I want to do is I want to solve for my original. Now, in terms of algebra, I know that because the original is being divided by, or the diagram is being divided by the original, if I want to move this one away, I need to multiply it out of both sides. So essentially I'm going to end up with original times by scale factor squared is going to be equal to, and I'm not going to write it out here, but I would multiply the original by this side as well, which would cancel itself out because original divided by original is 1. So diagram is left on this side, and now because I want to get this original on its own, I need to divide out the scale factor squared. So I'm going to say my original is equal to, so if I divide it out on this side, it's going to cancel out, so I'm not going to rewrite that out, but it's going to be equal to my diagram area divided by my scale factor squared. Okay, so now I can just plug in the math. The original is going to be, my diagram was an area of 25 centimeters squared. And I want to divide that by my scale factor, which was 0.1, which was also squared. Sorry, just to be clear, that's the units are squared. They're not the actual number. So if I do 25 divided by 0.1 squared, then I should end up with 2,500 centimeters squared is the area of the curtains. Or actually, I guess we should say that more clearly, is the area of fabric she needs. Fabric needed. Okay, so that's our final answer there. All right, let's look at one more example of this. So Jim's laptop has a monitor with dimensions 8 inches by 10 inches. The image on his laptop is projected onto the screen of the whiteboard. According to the documentation for the whiteboard, its screen area is 3,380 inches squared. So the first thing that we need to do here is determine the scale factor used to project images from the laptop onto the whiteboard. So keeping in mind that our scale factor is going to be our diagram divided by our original, and in this case the whiteboard is basically our diagram. Okay, so we have the area of the quote-unquote diagram, the whiteboard. So but we only have the dimensions of the laptop screen, which is our original. And of course, if we want to determine scale factor, we need to have both in area. So that's kind of a good thing to be aware of, is when you're calculating scale factor, you need to have either both linear dimensions or both sets of areas. Okay. So let's first of all calculate the area of the monitor, which is going to be nice and easy because, as we know, with a rectangle, area is always length times width. And so we have 8 inches times by 10 inches, which is going to give us 80 inches squared. Okay, so now that we have the area, the next thing we want to do is determine the scale factor. So remember, scale factor squared is equal to our diagram area divided by our original. Okay, so basically that means we can plug in the numbers. Remember, because we have this square here, we want to get rid of that. We're going to have to square root this component here. So we're going to say scale factor is equal to the square root of, let's see, what was our diagram area, was the whiteboard, so that's 3,380 inches squared, divided by the area of the monitor, the original, which was 80 inches squared. Okay. And so if we do that math, we should end up with a scale factor of 6.5. And it's actually a perfect decimal like that, so we don't have to do any rounding. So now that we know our scale factor, they want us to determine the dimensions of the whiteboard. So basically all we need to do then is figure out, we already had the area, but now we can use our scale factor for our linear components. So basically we would just say, in order to determine the diagram, it's going to be the original times by the scale factor. Okay, and so basically we can say one of the dimensions there was, original dimensions was 8 inches times by 6.5 is going to give us 52 inches. And then the other dimension there was 10 inches times by 6.5 is going to give us 65 inches. And so we can say the whiteboard is, whiteboard is 52 inches by 65 inches. Okay, and that is everything for working scale factor for area. So you guys have a little assignment to work on from the textbook there, and then when you're finished with that, you can move on to 8.5 and 8.6 is going to be our next lesson, where we're going to look at scale factors with 3D objects. So I will see you then.